Good day and welcome to the second in a series of 8 lectures. Today's topic is basic design considerations, and this lecture is hosted by Project Solutions Limited. Project Solutions are engineering, design and project management company with offices in Yorkshire and Teesside. My name's Brian Lawson. As well as working for Project Solutions as the technical director, I'm also the chair of the IMechE Western Area Committee. The series of lectures has been supported and organised locally by Nikki Baxter of the IMechE. So without all of her hard work, none of this would happen. But today, or for this full series, we're collaborating with colleagues in HQ in Birdcage Walk. So thank you to Lucy Esmond's team. We've got Fiona Wong supporting us today with the webcast platform. We have previously run these lectures for the Yorkshire region and have proved very, very popular. We get excellent support from Spirax Sarco in the form of Dan Wells, who does a brilliant job delivering the lectures. So keep it up, Dan. Additionally, with this series, we've got Stephen Bishop, one of Dan's colleagues, and he'll be helping to answer questions through the lecture. The questions can be asked by pressing the Ask a Question button, and Steve will deal with those as they come in. He may push them back out through chat, or if not, they'll be covered at the end of the lecture by Steve and Dan. The lecture will be recorded today and will subsequently be posted on the IMechE's YouTube channel. Anyone wishing to get more involved with the IMechE, that would be really great. You can give me a call on 0742 790 7716, or you can follow the link on the IMechE website. It's really great to get more people involved with volunteering. So without further ado, over to you, Dan.
Great. Thank you very much for that introduction, Brian. Much appreciated. And thanks also to Nikki and Fiona from IMechE for supporting today. As Brian rightly mentioned, we are joined today by my colleague, Steve Bishop. So if you do have any questions as we go through today's presentation, please feel free to take advantage of that opportunity. And I'm sure Steve will also embellish some of the comments I make as we go through the presentation. So please do keep an eye on that chat box. And as Brian rightly mentioned, today's presentation is the second in the series of 8 presentations that we've put together for you over the coming weeks and months. 2 weeks ago, beg your pardon, we did touch on the subject of steam system fundamentals, the basic steam generation criteria, and we looked at the basic properties of steam that set it aside as a very, very attractive source of heat energy. And hopefully it gave some very, very useful insights into why we need to treat steam completely differently to other sources of heat energy, such as low temperature hot water or thermal oils. And as we go through the remaining presentations, we'll look at different aspects each week, ranging from the topics of heat exchange and steam trapping to steam quality and condensate management. So just a little bit of a further introduction to Spirax Sarco for the benefit of those of you who may not have had the opportunity to join us 2 weeks ago. Spirax Sarco are a global organization. We've got our HQ in Cheltenham, but we've got a number of different operating companies, sales officers, and a significant number of direct engineers that are able to assist you wherever in the world your client or your offices may be based. And we'll come on and we'll touch on a number of those different operating companies and what they can offer in the coming weeks. As far as here in the UK is concerned, our operation in the UK is a team that's about 180 strong. About 50% of the team are field based. So we're always on hand to support any engineers that may require any support out and about on site. But the one thing I would like to draw your attention to is the fact that we've got a lot of very, very useful calculators and configurators that you can access on our desktop website itself. A lot of useful tutorials, sizing tools, and so forth. But of course, for those of you that are out and about on site, it's far, far more user-friendly for you to download the same series of calculators and configurators in the form of a very, very useful app. You can download that app free of charge to your iPhone, to your Android phone, and you can take those tools, calculators, and configurators out and about with you. So it's some very, very powerful information for checking steam pipe work, condensate pipe work, control valve sizing, steam velocities, steam trap capacities, cost of steam and condensate, for example. So I would encourage you to download that app, but please make sure that it's the Spirax Sarco Mexico app that you download. There's far, far more functionality on the Mexican app than there is on the UK and Ireland app. And of course, you can change the language back to British again. So on with today's presentation, and as you can see, the second in the suite is titled Basic Steam System Design Considerations. And basically this continues from the presentation that we went through 2 weeks ago, when we looked at the fundamentals of steam, the properties of steam, how steam's generated. And this particular presentation is going to focus on how we need to correctly distribute steam from the point of generation to the point of use. And as you remember, that distribution network can be hundreds, if not thousands of meters in length. So we need to get it right. So one of the first things I want to do is to take a very, very quick recap of the presentation we went through 2 weeks ago. And I'd like us to take a look at the properties of steam and the advantages that that brings. So we know that steam's a gas. And we know that that gas is compressible. That means if we generate the steam and distribute the steam at a high pressure, we will have greatly reduced the volume. We'll have compressed that mass of steam down. So that means that we can distribute that steam in a gas in a network that is relatively light in weight compared to, for example, if we were distributing that steam at a much, much lower pressure. If we had steam existing at a lower pressure, it would have a greater volume. We would need to distribute it in a larger pipe diameter. And another condition of steam being a gas, well, we don't pump gas. Gas moves in accordance with the pressure drop around the network. So if we're generating steam at a high pressure in the boiler, if we're consuming the steam hundreds or thousands of meters away at a much, much lower pressure, the steam will move in accordance with the pressure drop. So what's the advantage there? Well, the advantage is we don't need pumps. If we compare a steam system to a low temperature hot water or thermal oil system, well, we need to pump hot water. We need to pump thermal oils. So this is a significant cost involved with the capital expense of the pump, the installation, the maintenance, the energy required to move the heat from the point of generation to the point of use. None of that is required with a steam-based distribution network. We also know that steam as a gas, it's got that direct pressure to temperature relationship that we spoke about last week. So that basically means it's very, very easy for us to determine the temperature that the steam arrives at the process at simply by manipulating the pressure. And we also know that there's a significant amount of heat energy contained within a mass of steam. If we compare a kilogram of steam to a kilogram of low temperature hot water that may be designed to give up 11 degrees of temperature at the process, there's going to be as much as 50 times more heat energy in that kilogram of steam. And that's really got its basis in the understanding that water, which is the raw ingredient of steam, water has got a specific heat capacity of 4.19, meaning that if we want to increase a kilogram of water by 1 degree, we need to put 4.19 kilojoules of energy into it. And other properties of steam that make it a very, very advantageous source of heat energy for heat transfer, as we've mentioned, it's a gas. That means that it gives up its heat energy equally and evenly across the entirety of the heat transfer surface area. meaning we only need very small compact heat exchangers, and meaning that therefore it's going to be more advantageous by reducing the footprint of space we need to set aside for a heat exchanger. We also know that the speed of heat transfer is approximately 2 to 3 times greater than that of water. And that's principally because steam gives up its heat energy by condensing, by changing state from a gas to a liquid. So I want to just very, very quickly go across the steam tables. This is a slide that you'll recognize from the presentation we went through 2 weeks ago. It's perhaps the most important slide that we need to go through whenever we're discussing steam. So over towards the left-hand side of the screen, we've got what we refer to as the steam tables. Towards the right-hand side of the screen, we've got the temperature enthalpy curve. So as we discussed last week, the steam tables show us a lot of very, very powerful, very important information. The first column, that shows the pressure. It could be the pressure that the steam is being generated at in the boiler. It could be the pressure that the steam is being distributed at in the network, or it could be the pressure that the steam is being condensed at in the heat exchanger. Let's take the example of steam being generated in the boiler. If the pressure in the boiler is 0 bar gauge, well, we know that at 0 bar gauge, water boils at approximately 100 degrees. And we also know that the temperature of the boiling water is the same as the temperature of the steam. So when water boils at 100, the temperature of the steam is also 100. Do you remember that specific heat capacity, 4.19? Well, if we want to increase a kilogram of water by 100 degrees, we need to multiply the specific heat capacity by 100. So this next column demonstrates the amount of energy we need to put into that water to bring it up to boiling point, 419 kilojoules for every kilogram. But if we want that water to evaporate and produce steam, we need to put more energy into it, the enthalpy of evaporation. The next column, well, it shows us the sum of the two previous columns. That's the total heat energy present within the steam. And the final column, that shows us the volume that steam exists at under the known pressure. Now, when steam gives up its heat energy and condenses, it's actually the column that is demonstrated here. It's the energy that we added to that boiling water to make it change state to steam. That's the energy that's used by the process. Therefore, when steam's given up its heat energy, when it's changed phase from a gas back to a liquid again, the energy that is held back in the condensate is basically what's left behind when the enthalpy of evaporation has entered the process. So there's a lot of very, very powerful information here, and it demonstrates how all of these values change when we increase the pressure. And it's for this reason that we encourage you to download that little app wherever possible. It'll help you make sense of it very, very easily. But this particular presentation is about the design considerations that we need to take into account when we're moving the steam from the point of generation to the point of use. And you'll remember from the presentation 2 weeks ago, we mentioned that the biggest enemy of a steam distribution system was wet steam. So we want to keep the steam as dry as we can. So let's move across to the temperature enthalpy curve that we can see here. And this demonstrates the journey that water takes as it changes state and evaporates to produce steam. We're using the example here of 0 bar gauge, where we know that water boils at 100 degrees. And where we know that means we need to put 419 kilojoules of energy into the water before it will boil. So it's at this point here that the water is going to start to evaporate and start to produce steam. But it's only when we've added the full 2,257 kilojoules of energy into that boiling water that we can say that the evaporation process will end. We now no longer have water in the boiler. We've got 100% dry saturated steam. And that tells us that once we've added the full enthalpy of evaporation to the boiling water, we can see what the total heat content is here. So dry saturated steam, critically important. The term saturated, it means the steam's saturated with energy. It's physically incapable of holding on to any more energy than is demonstrated in this column here. Dry, that tells us there's no moisture entrained within the steam. So if you think back to the presentation we went through 2 weeks ago, if for any reason our client wasn't on top of the boiler controls or the steam generation in the boiler house, we'd have wet steam. If the energy source, if the fuel was contaminated, we'd have wet steam. So we could be at risk of failing to put the required amount of energy into that steam to make it fully evaporate. In other words, the steam that is generated could be wet, and also it would fail to be saturated with energy. So it would actually exist at this point here on the curve. That's going to cause us a number of problems because we've got wet steam now. And as we mentioned last week, wet steam, if there's a significant amount of moisture entrained within the steam, it's more likely to condense out. It's more likely to give up its heat energy to the distribution pipework than it is at the process. So for example, if we've got a process that requires 9,800 kilograms per hour of steam, we're generating 10,000 kilograms per hour of steam in the boiler. But if we're losing 300 or 400 kilograms of steam, if it's giving up its energy to the distribution pipework and condensing, then we're at risk that we're not going to have enough steam to satisfy the process. The heat exchange rate could extend and extend, causing a problem with the process, or it could well be that we simply fail to hit the required target temperature altogether. And if we've got an excess of liquid condensate that's held back in the distribution network, we need to remember there's far, far less energy in a kilogram of condensate than there is in a kilogram of steam. So we need to get that liquid condensate away very, very quickly. We do that by passing it across steam traps. So the wetter the steam, the more condensate there is, the more steam traps we need to design, engineer, install, procure, maintain, and so forth. It also means that if we've got a significant amount of condensate held back into the distribution pipework, well, it means that we're at risk of a little bit of corrosion of the pipework and the other ancillaries as well. That's going to require an ongoing burden of maintenance. And it also means that we may get specks of rust or corrosion entrained within the steam. If we're distributing steam at a fast velocity, we're at risk that the steam could pick up drops of moisture. And if that moisture becomes entrained within the steam and conveyed at a fast velocity, we're at risk of erosion or abrasion of sensitive areas like control valve seats, pressure reducing valve seats, flow meters. And that's not only going to cause damage that can be quite costly to repair, it also means that it won't be performing the function it's intended to do accurately. That can have an impact on the process. Any steam that's passing across a trapped puddle of condensate is going to have more of its energy drained out of it, so the steam is going to degrade. But it also means that if we get a fluctuation in pressures in the steam pipe, we're at risk that that condensate can be pulled up into a solid mass. And if that solid mass of condensate is released very, very quickly, that can result in what we refer to as water hammer, crash, bang, vibration, damage to the capillary equipment. So we want to convey the steam from the boiler house to the point of use to protect it, to ensure that we don't have a reduced mass of steam. We don't have a mass of steam with a reduced energy content, that we're not exposing the system to any erosion, corrosion, or water hammer. So the other physical properties that we spoke about 2 weeks ago were, first of all, that pressure to volume relationship. It reminds us that steam's compressible as a gas. At atmospheric conditions, 0 bar gauge, because there's no compression on the steam, it's going to exist at a volume of 1.673 cubic meters. If we generate the steam under a high pressure and distribute it under an equally high pressure, then we've reduced the volume. So we've got a significant cost saving by reducing the infrastructure of the pipework. But it's important to remember that when the steam falls in pressure, then the reverse will happen. We're going to get a sudden expansion of volume. So that tells us why the pipe sizing is critically important. And we've also got the pressure to temperature relationship that we've spoken about. If we increase the working pressure of the steam system, we're keeping the temperature at a high point. If we want to condense the steam at a low pressure at the heat exchanger, all we need to do is reduce the pressure accordingly. And that tells us why we only need a 2-port valve. If we compare it to a liquid-based system, the heat exchanger would typically require a 3-port valve, with the 3rd port being to divert away any energy that wasn't required by the process. So just looking at the boiler house, we looked at a few critical components in the boiler house that helped us to ensure that the steam generation was held at an optimum point. And we looked at a few of the key components, and one of the areas that we focused on 2 weeks ago was the atmospheric feed tank, also known as the hot well. Now, we've already mentioned that condensate, that hot water, it doesn't have any value at the process because it's got nowhere near enough heat energy to keep the heat exchanger at the operational conditions, but it's still hot water. So if we can recover that hot water back to the boiler house, we can keep it in storage in the hot well until such a time that the boiler requires hot water in order to keep up with and match the required amount of steam for the process. The hotter the water going into the boiler, well, we're going to see a number of benefits. First of all, hot water going into the boiler means we're not going to get thermal shock on the boiler as we would do with colder water. It means we're going to produce steam more responsively, more rapidly compared to colder water. It means that we need to consume less energy to generate steam than we would do with colder water. But another key benefit is at a higher temperature, well, the water will be capable of holding on to far less oxygen and other non-condensable gases. That can typically cause pitting and corrosion within the boiler itself. So an ideal sweet spot is around about 85 degrees. Any colder, we need to add more chemicals to purge off the oxygen. And of course, we're not going to get a responsive boiler producing steam at a financially attractive rate. So one of the first things we want to do is to make sure that the water within the hot well is kept as high as we possibly can. We also looked at the boiler level controls last week, and we mentioned that boiler level controls were required to ensure that we got the correct mass of water being brought into the boiler to keep up with the steaming output, and also to send an alarm whenever the boiler water level reached a dangerously low point. But what you'll remember is we mentioned there were a different series of sophisticated controls. They could be magnetic float, conductivity, or capacitance probes. They all have a different daily and weekly test and maintenance regime, and they will be sending a signal to either an on-off pump or a modulating pump. And what you'll remember is as we increase the sophistication of the level controls and the pump configuration, it means we're more likely to be in a position where we're distributing a condition of steam that is of a better quality. If we've got a lesser sophisticated control, for example, a magnetic float sending a signal to an on-off pump, that means we're more likely to get that wet steam that we want to try and keep away from. And last week, we also spoke about the blowdown controls. You'll remember we perform blowdown in 2 different areas of the boiler. We've got the bottom blowdown, where we purge a mass of hot water away to waste, typically once every 8 hours, once a shift, as a means of keeping the sediment out of the boiler. And we also perform what we refer to as the TDS, or the total dissolved solid blowdown from the side of the boiler. That's the solids that are held in solution, if you like. And the reason we do that is to ensure that we don't get an excess of foaming within the boiler. You'll remember that an excess of foaming, especially when it's drawn out of the boiler into the distribution pipework, can result in an excess of scale. And that scale is not only going to contaminate the steam, it's going to make the steam wet, where we know we've got less energy present within the steam. But that dried out scale can also bind itself to heat transfer surface areas, and it can also cause a significant amount of erosion of those sensitive areas in control valves, flow meters, and so forth that we've spoken about. So we can control the TDS and the bottom blowdown manually, and unless we specifically advise the boiler manufacturer of our requirements, manual blowdown controls are likely to be provided. But that makes it very, very difficult to accurately determine exactly how much blowdown is being performed. So an excess of blowdown, it can mean we've got a lot of energy going to waste, but too little blowdown can mean that we're likely to get a lot of scaling and a lot of foaming drawn out of the boiler and into the distribution pipework. The good news is that, as with the level controls and the feed pump configurations, the blowdown controls can very, very easily be retrofitted and upgraded to ensure that not only are we moving towards a fully automated boiler house, but it also means that we can produce a consistently better condition of steam and ensure that the steam is going to be produced far, far more efficiently from a financial perspective. We also mentioned last week that at the boiler house, well, we know that hot water does need to go to waste, but we also know that certainly as far as the TDS blowdown is concerned, because there isn't an excess of particulate present in it, it's in a good condition for being passed across a heat recovery solution. And of course, that means that we've got another means of helping to keep the water in storage in the hot well at a nice high level. So one of the last things we also want to keep an eye on before the steam leaves the boiler house is the exact mass of steam that is being produced. And that's going to help us for a number of benefits. First of all, it's going to help us to understand the true efficiency of the boiler operation itself, the true cost of steam. But by metering the steam as it arrives at the various processes, well, it also means we can keep an eye on any losses that may occur as the steam travels around the distribution loop. So please remember those guidance documents that are written by the health and safety executive, and they will focus on a number of key areas within the boiler house itself. For example, the level controls, including the testing, the supervision that is required on a daily, weekly basis, and also the various blowdown controls as well. And the thing to bear in mind is these guidance documents, they do focus on the safe operation of the steam boiler itself. And that explains why there are so many different configurations of controls. Really depends upon what's important to the client and the process. But please remember, the health and safety executive, they are only interested in the safe operation of the boiler. If you want to improve the overall efficiency of steam generation, if you want to ensure that you get a consistently good condition of steam being produced, then we do need to move away to a more sophisticated series of controls. So even when we are generating an excellent condition of steam, if we've got the best controls, the best water quality, producing an excellent condition of steam, it all means nothing if we're not observing good working practice in how we convey that steam from the point of generation to the point of use. And that's why it's important to give thought to those good design, those good basic design considerations. So whenever we're distributing steam from the point of generation to the point of use, we need to remember that that run of pipework, it can be hundreds, if not thousands of meters in length in the case of larger oil refineries, for example. So there is an opportunity there for that excellent condition of steam to degrade. And if we get a poor condition of steam at the process, well, we've really wasted our time in being on point in generating a good condition of steam in the boiler house. So when we talk about a good condition of steam, as far as the distribution pipework is concerned, it means we want the steam to be as dry as possible. That means removing that liquid condensate across a steam trap so it can drain away. It means we're protecting the system from an excess of rust, and it means that we're keeping the energy content of the steam as high as possible, as well as preventing an excess of erosion or water hammer. We want to move any particulate that may be present within the steam. That's why we use those little Y-type strainers that you may be familiar with. We want to remove any air and other non-condensable gases from the steam. We want to ensure we're observing good working practice so we can safely isolate key components. And most importantly, we want to ensure that the pipes have been sized correctly. Reason being, well, as we've mentioned, steam's a gas. It moves in accordance with the pressure drop around the network. So we want to ensure that we can get the correct mass of steam through the pipework at the correct pressure to satisfy the process. So as we can see here, the little graphic demonstrates the advantage of keeping that pressure as high as we possibly can. An advantage of doing so means that, well, we've compressed that volume down so it occupies a very, very small space. So we can distribute a high pressure steam in a small diameter pipework. And of course, if we're distributing that steam hundreds or thousands of meters, we're going to get a significant cost saving. But there's another cost saving that's often overlooked here. If we've reduced the pipe diameter, we've reduced the space that the steam can give up its heat energy and condense at. We've reduced the heat losses. So we've increased the overall efficiency. We're increasing the mass of steam that's actually going to find its way to the process. And we get far, far drier steam. We get less erosion, corrosion, and water hammer. And if we've got less condensate in the pipework, we need to install a lesser number of steam traps. So that means fewer steam traps to maintain and operate and inspect on a regular basis. So it's a win-win. We want to keep the distribution pressure as high as we can. So there are a number of different methods we employ when it comes to sizing the steam pipes correctly. It's really down to how far the distribution pipework actually is. So if we're distributing the steam over a long distance, we'd size on what we refer to as the pressure drop method. That's to ensure that we can get the required mass of steam distributed to the process at the required pressure. But for smaller runs of pipework, typically 50 meters and less, we would size on what we refer to as the velocity method. In other words, it's the speed that we're distributing the steam at. And there are typically 3 different speeds or velocities we would use: 15, 25, and 40 meters per second. It all really depends upon how wet the steam is, how much particulate there was likely to be in the steam. So if we were assured that we'd got an excellent condition of dry steam with no particulate in it, then we may be tempted to move towards the 40 meters per second velocity. If we knew for a fact that we got very poor condition steam, it's likely to have a lot of moisture and a lot of particulate in it, we'd want to be conveying that at a much more gentle velocity, 15 meters per second. The average would be somewhere between 25 and 30 meters per second. If we were distributing the steam at too fast a velocity, then that's when we're at risk that the moisture and the particulate would create a lot of erosion of those sensitive areas. So for example, if we saw a repeated failure of a control valve or a flow meter, it may be down to no other reason than the pipework upstream of the solution was conveying the steam too quickly, and therefore it would be undersized. So we can go back to first principles and use the charts that you can see on the screen for sizing the pipework. But of course, you can also download that little app that we've spoken about. That will help you gauge if the steam pipework, if your network has been correctly sized very, very easily. And there are other things we need to do to ensure we're observing good working practice in conveying steam as a gas. So over towards the left-hand side of the screen, you can see what could be considered good working practice on a liquid system. But on a gaseous based, on a steam system, that good working practice wouldn't ring true. We shouldn't be using concentric reducers. We should be using eccentric reducers with the level plane on the bottom. That way, any trapped condensate can drain freely and easily to a steam trapping station. Similarly, we want to ensure that any condensate doesn't become trapped at a low point. It can drain away, again, across a steam trapping station. And whenever we're locating a Y-type strainer in the distribution pipework, we want to ensure that the downward pointing leg that would otherwise become a point for condensate to become trapped, we want to ensure that it's become rotated so its leg is at 90 degrees. And as you can see here, the condensate can then pass freely and easily across the strainer to a point where it can be drained away. If we didn't observe this good working practice, condensate would become trapped in the distribution network. And it's at that point that we're exposing ourselves to that erosion, corrosion, water hammer. Steam's going to become degraded and have less energy in it. Another good working practice, well, it means we want to see a fall in the distribution pipework. And that fall wants to be in the direction of steam flow, to a gradient of approximately 1 in 100. Now that can be difficult to guarantee, but as long as we can see a fall with the naked eye, then we should be satisfied that the condensate can drain under its own motive energy to a low point, steam trapping station, where it can be drained away. And there's a correct methodology for designing a steam trapping station and a dirt pocket, as you can see down here in the bottom corner of the screen. And those steam trapping stations should be located somewhere between every 30 and 50 meters apart in order to ensure that we're keeping the steam dry. You can also see that there's good working practice here to ensure that when we're taking the steam pipe away to the process, we're doing so from the top of the pipework, where the steam is at its driest and therefore at its best condition. And we also mentioned that we want the steam to be kept as free of air and other non-condensable gases as we can. So we treat the water in the hot well with chemicals to purge off an excess of air and non-condensables. But the purpose at that point is to protect the boiler from corrosion. In the distribution pipework itself, we're always at risk that air is going to be present, because when steam condenses, its volume collapses and it can pull air in from the outside through vacuum breakers and control valves and gaskets, for example. So we need to ensure that we're allowing the air to escape whenever the steam is pressurized. If we weren't to do that, then sure, that air can create a little bit of corrosion of the pipework itself. But as we can see from the graphs in the middle of the screen here, a presence of air has got perhaps the biggest insulating barrier against heat transfer. So we're likely to get an inefficiency and a slowdown of the process. So we want to locate an air vent at the very, very end of the distribution pipework, at the occasional high point around the network, and at the process. So when the steam is pressurized, the colder air can be pushed away across a thermostatic air vent. It's got to be a thermostatic air vent. If we were to use a mechanical air vent, it would fail, because steam and air have got very, very similar densities, but of course they've got different temperatures. Safe isolation is also critically important. As we've mentioned, steam valves are typically metal to metal seated, so there's a risk that unless we've got an excellent condition of steam, those valve seats, they can become eroded, and it's at that point that we're likely to get a bypass of high pressure, high temperature steam. So if we've got a failing single isolation valve, there's a health and safety hazard. By moving towards a double isolation, where we'd got 2 valves in sequence and a little bleed valve between the 2, we're protecting the operator at the process that's performing that maintenance, and we've also got a little telltale that we've got steam being vented away. What we can also do here is we can bring all 3 of these valves together into a single casting. That means it's very easy to take a single isolation valve out and replace it with safe isolation within the original valve face to face. It's very quick and easy to upgrade that health and safety amendment. We also know that insulation is critically important and it's often overlooked. And the primary reason for that insulation is actually for health and safety. It's so that we don't have anyone banging the head or putting the hand out against a hot pipe work. But we also remember that if we've got let's say if we've got an oversized steam pipe, if that oversized pipe is running a significant distance outdoors on a very, very cold day, we're going to get a significant amount of heat loss there. And if we get a significant amount of heat loss, we've got a lot of condensate. It means we've got a financial inefficiency. It means we've got a lot of condensate to remove. It means we're more likely to get erosion, corrosion, water hammer, and degraded energy in the steam. So the good news is that if we're able to increase the grade of the insulation significantly, we can reduce those heat losses. So we're going to get an overall financial benefit for the client, a benefit for the time of the process. We're also going to get a significant benefit by minimizing that erosion, corrosion, and water hammer effect. So we've got calculators and configurators on our website that can give you an indication with regards to what the effect or what the payback is going to be simply by increasing the grade of insulation accordingly. We don't manufacture insulation, but we've got that tool that can help you understand what the effect of improving insulation grade is going to be. And similarly, we don't manufacture pipework expansion, but we know that it's vitally important that you consider the effect of expansion. Again, steam distributed at a high pressure, high temperature in a steel pipe over a considerable distance, it means that the network will be exposed to a little bit of expansion. So we can give guidance with regards to how much expansion can be expected. And from then on, you can speak with the stress analysis and they will give you a little bit more informed information with regards to how and where you can mitigate against that expansion. One of the reasons why we always encourage you to bring a steam distribution network up to temperature very, very gradually. And similarly, we don't manufacture pipework support, but pipework support, again, is vitally important. And we know that steam as a gas is far, far lighter in weight than water is as a liquid. So you may be forgiven for thinking that we don't need anywhere near as many support centres. And whilst that's true, we need to make sure we don't have too few support centres, because if we did so, then we're likely to get sagging pipework. And sagging pipework is obviously a place where the condensate can then become trapped. And you've guessed it, we get the erosion, the corrosion, the water hammer, and the degraded energy content. So it's far, far better to ensure that we're supporting the pipework from below. And better still, if we can use a roller and chair configuration, that'll actually mean that we can allow for a small amount of expansion there as well, which will obviously be beneficial for the overall integrity of the network. So as we move closer and closer towards the process, another thing we want to do is to ensure that we're conditioning the steam. And by conditioning the steam, we mean removing the moisture. So we want to use a separator. And the purpose of the separator is to remove that entrained moisture for two key benefits. One, the less moisture there is in the steam, the drier the steam, the more energy. Two, it's that moisture that creates that erosion and that abrasion of capital equipment, such as control valves or pressure reducing valves. So the moisture, it becomes entrained on the baffles within the separator, it condenses, it's taken away across a steam trap. The dry steam leaves the separator, passes across a Y-type strainer that you can see here, and then we know we've got a good condition of steam moving on to the process. Steam conditioning is very, very often overlooked. It's taken out and never replaced, or it's value engineered. And it can have an enormous impact on ensuring that the process is working efficiently, ensuring that we don't get capital equipment damage to the various valves and flow meters, and ensuring that we're not contaminating the heat exchanger with an excess of rust or scale that can create a barrier to heat transfer. So please just check, just have a look if you've got any capital equipment that has got these conditioning ancillaries missed. It can have a hugely positive effect. And as soon as the steam leaves the conditioning equipment that you can see here, then that's when we want to control the pressure. And we can control the pressure ahead of the process, either by using a self-acting pressure reducing valve, or we can use an actuated control valve for that purpose. If it is actuated, could be pneumatically or electrically actuated. The benefit of a control valve over a self-acting valve is that it will work a little bit more accurately. It'll respond to the process conditions in a more timely fashion, and it can send a signal back to a PLS or a PLC or a BMS. Common problems that we often see with control valves are these conditioning ancillaries are missed off, at which point, if we're exposing the control valve to wet steam, we will get that erosion. It means that we're not controlling the steam efficiently. That can impact the process, and it can have a financial inefficiency, and you could forever be replacing the internals of that control valve. We also often encounter control valves that are oversized, and when that happens, then the control valve internals will be operating far, far closer together, and that's only going to cause a greater effect of that erosion that we were speaking about. So we always size a control valve on the mass flow rate of steam required by the process, never on the line size. But of course, we could use a self-acting pressure reducing valve to do the same function. Pressure is more suited to larger or stable loads that aren't likely to fluctuate too much, especially in a hazardous condition where it may not be possible to have the electrical components. And we also know that at that point, it's worthy of consideration to ensure that we've got a safety valve. And the purpose of a safety valve is to protect the process and anyone that may be in that atmosphere, in that area, from any overpressure. So it's important to ensure that a safety valve has been sized correctly, it's been sized at the appropriate pressure, and it's been installed correctly. And by installing correctly, we mean in the vertical position. We don't isolate upstream or downstream of the safety valve. We ensure that the distribution pipework is kept to the shortest possible run, so we don't have an increase of back pressure on the valve itself, and to ensure that it's adequately supported, just to make sure that we don't have any pipework shaking loose if and when that safety valve is to pop. So of course, once we get the steam to the process, as we've mentioned previously, it's a great idea to ensure that we can meter the steam. And we do that for a number of different reasons. One, it's for process and quality control. Two, it's for process efficiency and fault finding. And three, it's so we can put a budget, we can put a financial consumption of steam on that particular process. And a steam meter can only work accurately and reliably if we've got clean, dry steam. We need to ensure that the steam is being conditioned in exactly the same way that that control valve should be conditioned. So we remove the moisture across a separator. We remove the air at that point. We ensure that that liquid condensate is drained away across the steam trap. If we didn't do that, then an excess of moisture in the steam, it would create that erosion and that failure that we've spoken about. The Y-type strainer to remove any entrained particulate, because if we didn't do so, we'd get erosion, we'd get a failure of the flow meter. Make sure we've got laminar flow. That means the required straight runs of pipework upstream of the flow meter and downstream of the flow meter, and to ensure that we've got a check valve installed so that when we get a backflow of condensate in event of a fluctuating steam pressure, we're not exposing it to an excess of water hammer. Again, many mechanical engineers may mistakenly believe that a steam meter is a fit and forget solution, but it will only ever work correctly if it is installed with the required conditioning ancillaries. So once we get the steam to the process, we need to understand that the steam needs to be distributed in accordance with what that individual process requires. So when we talk about a good condition of steam, we need to ask ourselves, well, what does good actually mean? If we're distributing steam for a heat exchanger in a rendering factory, or if we're distributing steam for a sterilizer in a hospital. They're going to mean completely different things. So different industries will measure steam condition in a number of different ways. Let's consider a high-end process where the steam could be exposed to a product or an atmosphere. That's where we want to ensure that the steam condition isn't at risk of contaminating an atmosphere or a product. We're going to want to use BSEN 285 to measure the steam. For example, we'll want the steam to be 95% dry or better. Why? Well, that means that we're not at risk of putting an excess of moisture into that product or into the atmosphere. And when we talk about moisture, we need to remember that that also means boiler chemicals. We want to ensure that we don't have an excess of air that's likely to be present in the steam. Air and other non-condensable gases, they've got an insulating effect. If we know the pressure of the steam, we might mistakenly believe we know the temperature and the energy content. But the presence of any air is going to have an effect of diluting that. We obviously want to ensure that we've got the correct temperature, pressure, and mass of steam to satisfy the process. And we want to ensure that we've got a mass of steam that is free from boiler scale or rust. So all of these things can be measured, and they're all going to be determined by the exact nature of the process. So once we've got the steam to the process, as we've mentioned, we need to ensure that we're distributing the best possible condition of steam. And that's the importance of observing the good basic design considerations to ensure that if we're generating a good condition of steam in the boiler house, it arrives at the process in the condition that is expected and required. So typical heat exchange processes, they could be what we refer to as a closed loop heat exchanger, where there's no risk of contamination arriving into that process, or it could be a direct injection system. And that's when we need to give a little bit of thought to the risk of potential contamination. And we're going to come on and talk about that in a little bit more detail in the next presentation we have in our series. So I'd like to thank you for taking the time to go through the presentation that we've put together for you today. Just want to really summarize very, very quickly that we know that steam is easy to distribute. It's a gas, but in order to distribute it correctly, we need to size the pipework correctly. We need to observe good working practice that wouldn't be applicable to liquid-based systems. For example, the fall in the distribution pipework. We want to ensure that we're trapping the steam appropriately to remove the condensate and keep the system as dry as we possibly can. We want to ensure that any little Y-type strainers, for example, are located with the leg on the side. We want to use those separators to ensure that the moisture is removed appropriately. Typically, we would do that immediately behind the steam boiler itself. But as far as the distribution network is concerned, we also want to be using separators ahead of sensitive equipment, such as control valves and flow meters, and immediately before it enters the process. But please remember that the biggest enemy of a steam distribution network is wet steam. So I'd like to thank you for going through today's presentation. The presentation that we have in 2 weeks' time is going to look a little bit more about how and where we use steam at the process, typically heat exchangers. And in coming weeks, we'll focus on different aspects such as trapping the steam and condensate management. Of course, for those of you that have got an appetite in understanding steam, learning about steam systems in more detail, here in the UK, we've got our own Steam Technology Centre down in Cheltenham, and we know that we've got different steam technology centres that can offer similar training courses in other countries throughout the world. So on that point, I'd like to thank you very much for your time today. Steve, can I ask if there have been any questions that need any more attention there?
Yeah, hi Dan, thanks. Another excellent presentation there as usual. Thank you very much. Very clearly put across There were a couple of questions. There's one that I've already answered, hopefully in a way that everyone can see in the public questions area there. So the first question that came in was regarding distribution under higher pressure. You mentioned distribution under higher pressure to get those infrastructure benefits. What is a good pressure for a steam distribution network? The answer I provided to that, which hopefully you agree with, was that we should aim to keep our steam as close to generation pressure as we possibly can in order to maintain optimum conditions. And then there's a further question that's just come in, which is, are there any particular types of meter that are more suitable for use on steam? And do you cover this in other presentations?
Good question. Yes, I will cover that on the energy and steam topic, which we will have on the 22nd of June. It really depends upon a number of different things. It depends on, first of all, the turn down that it's required to measure. That means the difference between the high load and the low load that the steam meter will be required to measure. It depends upon the accuracy that is required, and it depends upon what we refer to as the repeatability. In other words, accuracy, as the term, as you may expect, is the ability for the meter to read a true and accurate reading. Repeatability is the ability of the meter to read the same reading time and time again. So accuracy and repeatability, they sound the same thing, but they're not necessarily are. So there are a number of different things that we need to take into account. Certain meters can be installed inobtrusively. Certain meters will need a certain amount of conditioning ancillaries to be used. It also depends whether we're metering the boiler water, the steam, or the condensate itself. There are a number of different considerations, but again, we will look at those in a little bit more detail on the 22nd of June.
Okay, brilliant. Thanks, Dan. So no more questions at the moment other than those.
Thank you. Anything to add there, Brian? Okay, well, it doesn't sound like Brian's with us at the moment, but I'd just like to say thank you very, very much on behalf of Spirax Sarco, on behalf of projects, and on behalf of IMechE. If you do have any questions, please feel free to contact me on LinkedIn. I'd be more than happy to address anything that needs any more attention. But on that note, we look forward to you attending the presentation again in 2 weeks' time.